Welcome to e-learning portal of Bishopberg College. I am Dr.R. Venkatesh, Assistant Professor, PG and Research Department of Physics, Bishopberg College. Would like to share some of the brief ideas on Maxwell-Boltzmann distribution law. So, James Clerk Maxwell and Ludwig Boltzmann formulated a distribution law for the system of molecules in a vessel. So, according to the fundamental postulate, the total number of particles in the system is considered to be a constant, and the total energy of the system is also considered to be a constant, and we are actually following the microcanonical ensemble for this distribution law. In order to get the ideas on probable distribution of microstates of the system, we should know, or we should recap what is the actual macrostates and microstates of the system. So, just consider a simple example that I have 4 balls and 2 boxes, and I need to distribute these 4 balls into 2 boxes. It can be done in different number of ways. So, either I can put the 4 balls in one box and another box as empty, and the second distribution as 1 ball, 3 balls and 1 distribution, and then for the third distribution I can have the equal distribution of 2 and 2, and the next one I can have it as 1 and 3, and then for the final distribution I can have it as 0 and 4. So, these are all the possible number of distribution ways in which these can be done, but each and every distribution will be considered as a macrostate, and you need to consider each and every ball is individual. Actually, they are distinguishable by means of its color. So, if you just consider this, I have the macrostates listed here, and then the compartments you can have a different number of ways in which you can do this arrangement. For 0 and 4 we have only one option, but for the next one I can have a multiple. That means one is with A, another with B, C, D, and then another with B, another with C, D, A, and another with C, another with D, A, B, and then D, A, B, C. So, there are 4 combinations for 1, 3 alone, and similarly for the others also. So, as you can see that the 2, 2 will have the maximum number of combinations, and 3, 1 will have the similar type of combinations as the previous one, and 4, 0 as usual only 1. So, these individual combinations will be considered as a single microstate. Okay. Then now consider for our specific case. So, look at this. I have 3 particles, that means 3 gas molecules, and then I have a total energy of about 3E. Okay, for a system consisting of total energy of 3E, I am having 3 particles, and I need to share these 3 particles among the given available energy levels. So, on all the energy levels, you could see that I have a 0E, 1E, 2E and 3E, and for that I need to distribute these 3 particles. The possible number of ways, so I can distribute in 1E, all the 3 particles, and in another case I can put one particle in 3E and another particle in the ground state, and then I can put one particle in 2E, another particle in 1E and another particle in the 0E. So, in each of this you could consider that each and individual particle is distinguishable, which means that swapping a particle from this particular state to this particular state will give rise to a new microstate. Hence, we need to consider the possible number of ways. So, the possible number of ways, it can be obtained by 3 factorial, that is total number of particles factorial divided by the occupation of particles in each energy level. For the first case, only in 1E I have all the 3 particles, so 3 factorial by 3 factorial, and then in the second case I have the total number of particles 3 factorial divided by 1 particle in 3E, another particle in 2 particles in 0E, and then in the third case I have each particles in 2E, 1E and 0E. So, the total number of ways is, the first case is 1, another case is 6, another case is 3, and then the probable distribution, mean the probability of distribution will be 10%, 60%, 30%. So, from this we need to calculate the probability of finding the most probable distribution of a microstate. So, for this, in order to generalize this expression, so I have given this omega as the total number of possible microstates. So, omega is equal to n factorial, capital N factorial, total number of particles divided by the each number of particles occupying the energy levels. So, n1 factorial, n2 factorial, n3 factorial and up to Ni factorial, and it can be written as omega is equal to capital N factorial divided by it can be the product value is given as pi of I Ni factorial. And then for this the expression I need to, since the factorial of a many number, that means for a single system I can have Avogadro number of particles, which means 6.023 into 10 to the power 23 number of particles. So for this it's a very very huge value. In order for that I need to go for Stirling's approximation. So for that I am taking the log on both sides. So ln omega equal to ln n factorial minus summation of ln ni factorial, as the log a by b is equal to log a minus log b, and the product becomes summation here. And the applying the Stirling's approximation, ln x factorial is equal to x ln x minus x. So here applying this in the above expression, ln omega is equal to ln n factorial minus summation of ln ni factorial, and ln omega is equal to n ln n minus n minus summation of n ln ni minus ni. And then I am expanding this, and then finally you know that summation of ni is equal to capital N, and this n and this ni will get cancelled, and the remaining n ln n will be considered as a constant. So ln omega is equal to minus of summation ni ln ni plus constant. So the idea is I need to obtain the most probable distribution, and the probability should be very high. In order to achieve the maximum probability, the condition is that differentiation of ln omega is equal to 0. So I need to differentiate the above expression. So del ln omega is equal to summation of del ni ln ni. So differentiating this, ln ni plus 1 into del ni. So the condition of maximum probability is del ln omega is equal to 0, and I am equating this equal to 0, and I am removing the minus sign, and then these are the auxiliary condition that we have seen in the previous slides itself. So the total number of particles is considered to be a constant, and total energy is also considered to be constant. So del ni is differentiation of total number of particles, which is again a 0, and the total number of energy is also considered to be 0. So we have three expressions, that is, first condition is del ln omega. From this I have achieved summation over ln ni plus 1, del ni is equal to 0, and we have auxiliary conditions. We need to sum up all these three in order to obtain the distribution function. So in order to do that, we have to apply the Lagrange's method of undetermined multipliers. The reason is that we have to adjust some of the factors by means of some experimental errors or so that we need to add some of the Lagrange's method of undetermined multipliers. So in order to solve the previous three equations by summing up ln ni plus 1, multiplying this auxiliary equations with this one by alpha and this one by beta, and we get ln ni plus 1 plus alpha plus beta epsilon I into del ni is equal to 0, and the summation of ln ni plus alpha plus beta epsilon I into del ni is equal to 0. So as one is negligible, we can neglect that, and then ln ni plus alpha plus beta epsilon I is equal to 0, then ln ni is equal to minus of alpha plus beta ei. So we have to take exponential on both sides in order to remove the natural logarithm, and finally we will end up with the final expression of the Maxwell Boltzmann distribution law, that is ni is equal to 1 by exponential of alpha plus beta epsilon I. Okay, so beta ei, that is the energy, the total energy with respect to the given number of particles occupying a particular energy level. So this is the most probable distribution, and this is applicable for the gas molecules in a closed container or a closed vessel by means of applying the microcanonical ensemble idea. So I think this will be helpful for you in order to have a better idea on Maxwell Boltzmann distribution law and have a happy learning. Thank you.